All right. Thank you, Andrew, for the introduction, and good morning and good afternoon, everyone. Thanks for joining us in this presentation. Today, we are going to discuss what we have found and how we have created this MIT Streamline Pavement LCA to enable our pavement stakeholders to quantify the life cycle environmental impacts of pavements in different contexts. To start this presentation, I would like to bring this news piece to your attention that talks about the embodied impact reductions of different pavement types by incorporating recycled materials. Generally and notionally, incorporating recycled materials is considered as a good strategy to mitigate the GHG emissions and improving the circularity of the materials. But there is more awareness these days about this, that we have to think about the future and the consequences of our decisions when we think about the solution in order to mitigate our GHG emissions. For example, here it was stated that it might require more truck driving construction workers to maintain it, implying the importance of considering the frequency of the maintenance for those roads in the future, and also repair or replacements that we would see over the life cycle of a product. So we see the same approach when we look at the legislations, for example, the Inflation Reduction Act, that there are a lot of incentives around reducing the embodied impacts of the construction materials, including different types of pavement materials. As you can see, these are very well targeted to reduce the materials impacts reduction. But from a life cycle perspective, we see a lot of different opportunities in the construction, use, maintenance, and end-of-life phase of the pavement life cycle. For example, how much we can reduce the excess fuel consumptions induced by the surface roughness and deflection of the pavements. How can we improve the reflectance, the surface reflectance of the pavements in order to gain benefits in terms of the albedo effect? Or for concrete pavements, how can we improve the carbon uptake or carbonations in order to sequester a larger amount of CO2 from the atmosphere? From a maintenance perspective, it's a very important decision because it can determine the surface characteristics of our pavements. Like if you think about how we can wisely spend our dollar values in our pavements to get the most out of the pavement performance and make the surface smoother or improve the pavement condition, that's a very good question for improving the maintenance activities and including this in our legislation. Or ultimately, at the end of life, how can we improve the material circularity? How can we gain more benefits from recycling the pavement materials into other products or in other systems as well? So with reviewing the life cycle, we can see a very good perspective for low carbon policies. The first one, as you can see on the box on the left, impact of material choice on the rest of the life cycle. How can we engineer these materials in order to have a better performance during the construction, use, maintenance, and end-of-life phases? So thinking about different solutions from a prospective standpoint. And second, not only we can reduce the embodied impacts, but also we can think about current solutions that we have available to mitigate the use and end-of-life emissions. So these are two important policies that we can add to the embodied impacts calculations, for example, for buildings and embodied impacts reduction. And why is it important? These pie charts would explain the importance of considering the life cycle perspective when we make a decision. And it shows the proportion of the life cycle GHG emissions from different phases. As you can see, for both asphalt and concrete pavements, more than two quarter or 3/4 of the emissions comes from the use phase emissions relevant to the surface roughness, the deflection of the pavements. And there is around 26 or 1/4 from the material and construction, which we refer to as embodied impact. So it's important to think about this more holistically and from a life cycle perspective. But what do we need to do Here, we would need some tools, right, to quantify the environmental impacts of the pavements. There are many tools available from different authorities and universities, research centers, that includes and incorporates different life cycle phases and quantifies the environmental impacts, life cycle environmental impacts of pavements. We generally observe two shortcomings in this tool. The first one, which was very prevalent, was that in many tools, the use phase impact completely or partially excluded, meaning that the pavement vehicle interactions, the deflection and surface roughness induced fuel consumptions were excluded. The albedo effect or the carbonation weren't included as well. And in those tools that we have the use phase, we saw that they are relatively data intensive, meaning that they ask users a lot of data to quantify the life cycle environmental impacts, which makes the LCA cost prohibitive, both from the labor and data collection perspective. So to put it in a nutshell, we observed that there are three main gaps in pavement LCA that we covered in our Streamline LCA tool development. The first one is to deal with the cost and labor intensity of the pavement LCA. The second is about the extent of data that we need to input. And the last one is the uncertainty relevant to the future. Generally, whatever decisions that we make for the future deal with some level of uncertainty, and making decision under the uncertain condition and in capturing the uncertainty and embracing that would really help us to make a robust decision on the preferred scenario or preferred selections between different alternatives. And here at the MIT Concrete Sustainability Hub, we developed a streamlined pavement LCA framework based on the publicly available data. So these are some federal and DOT available data that we collected and we included in our tool and analysis. And we included a probabilistic comparative analysis to capture the uncertainty and give the decision maker a better confidence about the robustness of the results. I'm going to stop here. I'm going to hand it over to Dr. Hao-Ran Lee, who will explain the tool development and some of the lessons that we learned from the case studies in different locations in the US. Hao-Ran, the stage is yours.
Thank you, Dr. Azari Jafri. So thanks for the brief introduction of the research gaps of the Streamlined pavement LCA development. So here I'm going to start with the methodology we have been implementing for the development of the CSHub Streamlined pavement LCA framework, and the following the two development based on this framework. So the CSHub pavement LCA framework involved all the components of pavement LCA. So we have the embodied emission as well as the use phase emission consideration. To simulate the life cycle GHG emissions based on that, so we need to have the quantitative evaluation and computation of the material and construction emissions, which includes the raw material supply, transportation, energy, and fuel consumption. And for the use phase emission, we have embedded three sub-modules, which is the pavement vehicle interaction, which is PVI related to the deflection of the pavement, as well as the pavement surface roughness. In addition, we have embedded the model of the albedo, which is the reflective of the surface of pavement, as well as the concrete carbonation, which is also called CO2 sequestration. And for the absorbed of the data requirement to do this modeling and computation, for the design perspective, we need a paving material mixture design for both concrete material and asphalt material, which are mostly used for our pavement construction, and which here we have the pavement design alternatives, the GPCP and HMA design. In addition, the maintenance and rehabilitation, which is called M&R, which also is a significant component, will affect both the embodied emission because of the construction and the material consumption, as well as they will significantly affect the sub-modules when we are doing the use phase computation of the life cycle GHG emission. So in this case, there's extensive data are required to maintain this computation and payment design. So we have include different payment context perspectives, which include geographical location and the climate conditions of payment, including temperature, the rain, the moisture, etc., as well as the material properties for all the material we involved in our payment LCA analysis. In addition, the payment geometry, which is very highly correlated to our payment design perspective, at least the last but not least, the traffic loadings as a significant components affect our use phase and also the embodied emission because of payment design. And so we start with the payment design streamline. So here we have the most advanced payment design guide, which is very used in the US and Canadian, which is called Mechanistic Empirical Payment Design Guide. So which is also simplified as MEPDG. So this design guide has many benefits, but also it has some disadvantages for the user to directly implement, because first it needs the Pavement ME software as a companion software. The Pavement ME software requires extensive data from the user as well. There's more than 2,000 inputs from the user to actually perform a segment level payment design, which is complicated. In addition, the Pavement ME software is more like a payment analysis software. It analyzes the payment performance over a long time perspective, but also it cannot give a directly design optimization for this payment. And also to run the Pavement ME, there's a license fee, which may not be affordable by the local users. In addition, this is time-consuming software, which there needs several iterative design to find the optimized design by the user itself. So to solve this, we propose a surrogate modeling method to accelerate this payment design using MEPDG. So we propose to use a machine learning model as a surrogate modeling of payment ME simulations, which is we are using artificial neural networks to perform this surrogate modeling, and we perform sensitivity analysis to subtract the most sensitive design parameters for our neural network model training, and which is simple, and it can involve both the long-term payment performance prediction as well as the design optimization, which this is standalone modeling, which can be run without the further payment ME implementation. And in addition, which is this neural network SORM model, it's much faster than the payment ME software. So to do so, we start from the payment ME software simulation. We have been run thousands of payment ME simulations to build our database for the training of our neural network models. And after that, we embedded these neural network models in our Streamline payment LCA tool as a standalone software tool. And then we will be able to input our data directly to our payment Streamline LCA tool. And then we will be able to predict the different payment performance for both concrete payment as well as the asphalt payment, which include the transverse cracking and joint faulting for the concrete payment. And for the asphalt payment, we have the fatigue cracking, rutting, and thermal cracking, which align with payment ME direct output. So in this case, those payment in surface roughness can be computed based on the MEPDG guidelines as a synthetic indicator of the payment surface roughness, and they will significantly affect our design decisions. In addition, the MNR will also be involved in our Streamline payment LCA tool, which will happen during the payment surface life, which will also affect the payment roughness. At last, we can compare our payment LCA RI prediction with the payment ME prediction when we are using the neural networks for the prediction of the long-term payment roughness. So we can see here the neural networks has a perfect agreement with the payment ME prediction for long-term 50-year payment service life. But the neural network model only need a fraction of the computation time than the payment ME. to run a segment performance prediction, the neural network model, which only needs 0.02 seconds, which is much shorter than the 10 minutes payment mean simulation. So here we are introduced a beta version of our Streamlined payment LCA tool. So now it's under development with version 1.3. So here's the user interface as overall. There are the 3 steps to run the payment LCA analysis. So first, we'll be able to let the user to input their payment context information as we introduced in our framework, which include the locations of their payment and the climate data as well. In addition, the traffic data, for example, the traffic system, the function system, reliability of this payment design, as well as the detailed pavement track load, the ADT, and the track percentage, track growth rate, as well as the track speed, etc. In addition, in the next step, we'll be able to use this input payment context to design our payment, the thickness design, the geometry design, so which we have the capability now to enable the design using 2 design guide, H293 design guide, as well as the MEPDG design guide we just introduced. So in this case, we will be able to have all the design components directly as output of this tool for the further analysis of the payment LCA. So in addition, for the step 2.1 and 2.2, the material emissions will be computed for both materials for concrete and asphalt materials. So the mixture level pavement pavement GHG emission will be computed internally, as well as we will enable the user to input their own paving material mixture for their own local or project specific computation of the material emission as an overall indicator. So next, we will then be able to let the user to input their scheduling of the pavement maintenance and rehabilitations. So we have the default values, and also the user will also be able to input their preferred M&R scheduling during the life cycle. So last, we will see the results when we are running the payment LCA. So we enable the user to run a Monte Carlo simulation from 100 to thousands or more for its a probabilistic analysis of this payment LCA, because we know there's a lot of uncertainties within that analysis for example, 50-year long time life cycle analysis. So here we have this output as example. So the left panel, which is the medium inputs, which are observed from our input as a whole. So we also have our design 1, design 2 as an example, which are medium design for different payment design alternatives. Here we have a GPCP design and HMA design. So in the middle panel as output, which is our medium instance outputs, which we have the output for different visualizations. So we have the stacked bar chart to show the users, all the components contributing to the life cycle GHG emission, including the user phase, the use phase, as well as embodied animation. And also we have the individual output for these 2 designs. And the last, on the right-hand side, there's a payment conditions. We have a life cycle analysis of prediction of this RI performance, and can compare them simultaneously. So in the last row, there is a probabilistic and comparative payment LCA analysis for the both payment design alternatives. So you can see there's a lot of uncertainties and variations of the payment LCA analysis. But also we will be able to show the users the probability at the end of this figure. So the probability that which design may be preferable for a life cycle perspective. And so to do so, we have a structured data specifications, so which we could accommodate any data level to do this framework. So we have a specification level as 4 categories from M1 to M4. So from the left to right, M1 means that there's a general details with a broad variations of the input data. And from the M1 to M4, we have a specific details with limited variations of options. So as shown example in this figure, so for example, we have subgrade resilient modulus as our input. So when we have no information of the subgrade, we want to build our roll down. So we can assume they could be any soil types. So which these variations of the subgrade modulus has a very large variations, which could be from 5 KSI to 50 KSI. However, when we are knowing more information of the soils we want to build our pavement down, for example, if it's a salt clay materials, the relatively uncertainty will be reduced and the variation also will be reduced. And if we have more specific detailed information, for example, M3, we know it's clayey soil, and even M4, we know exactly it is a soil type of the definition of AASHTO A76 soil. We now know there's smaller variations of this because of the subgrade material properties of this typical soil. So then we will be able to shrink the variation from M1 to M4. So lastly, you can see this right-hand figure show the distribution of this one. So when we are shifting from M1 to M4, the relatively variation will be significantly reduced. And so here is the example, show the total framework. So we have our payment context, payment traffic systems, and payment structure design, material properties, and M&R scheduling. So in M1, for example, if we only know that this payment will be built in Arizona, and we have two payment design alternatives, which are PCC and HMA, and we know that it could be one M&R during this life cycle for both types of payment, but we have no other information. So we can also be able to run this payment LCA. But with the increase of payment details from M2 level, the user may know that there's a specific urban traffic system with standard grade concrete material, granular base, and granular material as subgrade, and HMA, we have a granular base and the same subgrade. And we know we may do a minor repair around the year of 28 to 40. So with the increase of the level 3, we know more details of the traffic and the material properties for both types of payment design alternatives. And we also know more details of the specific M&R's type and treatment we want to do. And with the year range will be shrink to 32 to 38 years. And furthermore, so we may know all the details from the users at the project level. So we also can accommodate all these specific data with specific detail numbers of each payment design or payment LCA components. So from the left to right, the least spec data will be moved until the most spec data. This payment LCA framework can accommodate any of them. So here the sample results as we just input from M level 1, we can see this figure. So the blue line is the design 1, the red one is the design 2. The top figure shows that the life cycle estimation, which starting from year 1 to the end of life, there will be a significant variations of both design because we know little information of them. And when we are comparing these two at the bottom figure show that, so which design is preferable, we can see that the uncertainties can distribute largely, and there's only like 75% probability that design 1 could be better than design 2 in the life cycle perspective. But when we are reaching design 2, M2 level, when we are knowing more information of this payment LCA work, so we know that this variation can be significantly reduced for both of this design. And when we are comparing now these two design alternatives, we saw that the design 1 has a 99.8% preferable when we are comparing design 2. And when we are reaching design 3, when we are knowing much more information for this project level, we will find that furthermore, the life cycle GHG emission variation has been shrinkage, and design 1 now has a 100 probability is preferable than design 2. And lastly, when you are knowing every specific data, you can also perform this payment LCA using this Streamline tool. And the preferable the design 1 is also 100 better than design 2 in a life cycle perspective. But however, if the user like do not have the M3, M4 level of the data, or it is time consuming for the users to get the data from the data source, the design, the M2 level is sufficient enough for the user to input limited data information, but can have a high confidence when comparing two design alternatives at this case study. And so another case study we want to show that is the capability of this Streamline payment LCA tool. So which we will be able to also use this payment LCA framework to improve our design as well as the scheduling of the M&R. So for example, here we have another example. It is a proposed payment design at Massachusetts State, which is the rural interstate system. The two-way AADT will be 38,000 with a 20% of track percentage. The segment level now is a segment length now is 1 mile. So we also have two design alternatives, which are structural equivalent. The design one is the GPCP BU business as usual. So it is a 10-inch PCC, 1.5-inch dot bar, 6-inch aggregate base, and 12 feet slab width. For the design two, we have 8-inch HMA surface layer and the 8-inch aggregate base and 12 feet slab width. So this is the medium instance from the output of the Streamline payment LCA tool. We can see that both payment has been maintained very well in the roughness perspective. So with GPCP has design one has 1 M&R about 25 years, and the HMA has 2 M&R during the life cycle. And when we are comparing the life cycle GHG emission, the design one has 7.6 kiloton CO2, and the design two has about 9.9 kiloton CO2 in life cycle. So we are comparing the probabilistic and comparative life cycle analysis results. So we can see that there also have variations because of the uncertainties with this input data, and we are also able to comparing which design is preferable. However, we can see that there is 22 years crossover, which means the design one has to wait 22 years to see the benefit, to see if compared with design two alternatives. So in this case, we are searching a potential solution to accelerate that crossover or beneficial time. So first, we try to improve the GPCP design, which we have tried different payment geometry design alternatives. As stated, our GPCP BAU has a 15 feet joint spacing, 10-inch PC thickness, 12 feet slab width, and 1.5-inch dot bar. So first, we try to reduce the joint spacing from 15 to 12. The other component remain the same. The third, we have reduced the piece thickness from 10-inch to 9-inch. And last, we have tried to increase the slab width from 12 feet to 13 feet. So 1 parameter at a time. So when we are comparing the life cycle GHG emission, so again, the HMA BAU and GPCP BAU will be serving as our baseline scenario. And when we are decrease the GPCP joint spacing, we can see that the life cycle GHG emission has been reduced, and because of the reduction of the PBI roughness, and also the GPCP, when we are reduce the thickness, we also has a slightly decrease of this life cycle GHG emission because of the slightly decrease of body emission. And the best strategy we have seen here is the last one, which we have the 3 parameters improvement. So in this case, when we are comparing our GPCP BAU, the last case we have been trying has reduced the 35% of the life cycle GHG emission because of this significant reduction of the PBI roughness generated GHG emission, even though with it, where is the slightly increase of the initial emission. And also when we are comparing to the HMA BAU, we saw there's a 50% life cycle GHG emission reduction. So we are comparing the beneficial time or crossover with our baseline. So we can see that originally it is 22 years, and now we can reduce the benefit time from 22 years to 14 years. And then we also try to improve the M&R scheduling to improve our GPCP for a life cycle perspective. So again, our M&R BAU, it was 100% dam grinding and 5% full depth replacement at the year of 25. So we have tried 4 different scenarios to scheduling our M&R. We have tried 4-inch bonded concrete overlay at the year of 20, and we also tried the 6-inch bonded overlay at the year of 20 as well. So we also tried the dam grinding alternatives. So we have trying 2 dam grinding as dam grinding multiplied 2, which happens at the year of 20 and 40. And the last one, we have trying 3 dam grinding, which are happening at the year of 15, 30, and 40 years respectively. So from here, we can see the result. So for life cycle perspective, we saw there's up and downs for different M&Rs. We saw there are several components, which, for example, the 4-inch bonded concrete overlay and 6-inch bonded concrete overlay has much larger emission from the M&R because of our overlay thickness. And as well as we can see that there will be reduced PVI roughness, induced GG emission. And also we can see that when we are doing dam grindings, so we do not introduce too much emission from M&R perspective, but we have reduced the PVI roughness emission when we are comparing to the M&R BAU. So overall conclusion, we have been seeing that when we are comparing the best scenario we have been seeing so far, the improved M&R as the last alternatives we have tried, which is 3 dam grinding, can reduce 22% life cycle GG emission as compared to the M&R BAU. And when we are comparing to our HMA BAU baseline, there's a 40% GG emission reduction. And then when we are comparing the beneficial time, so originally it was 22 years. And now the benefit time has been reduced to 18 years because of the improved M&R scheduling for the GPCP. Okay, so here's the takeaways for today's seminar. So we use the structured data analysis, which allows a statistically sound evaluations for the competing pavement design alternatives, even with less information. For example, we have M2 in our case study, which is enable us to make the decision with high confidence. And also we have been assured that the improved GPCP design can reduce the life cycle GG emission by up to 35% when compared to the original M&R scheduling, and by up to 50% when we are comparing to HMA design alternatives. And also it can shorten the payback time of GPCP from 22 to 14 years. And also we have been improved that the improved GPCP M&R scheduling can reduce the life cycle GG emission by up to 22% when comparing to original M&R scheduling for the GPCP, and by up to 40% when comparing to the HMA design alternatives. So we also show that it can shorten the payback time of GPCP from 22 to 18 years. So now I will hand over to Dr. Azari Jeffrey for the next steps of our Streamline framework and the tool development.
All right, thank you very much, Aaron, for this great explanation. And just as a reminder, Andrew posted it in the chat box, but please feel free to add your questions in the Q&A box below. I'm going to talk about the next steps that we have to build off of the current capacity at the MIT Concrete Sustainability Hub around the Streamline Pavement LCA tools. As you see, the tool is now based on MATLAB code. The general user interface is available. Please feel free to reach out to us. I'll share the email in the next slide if you want to install the tool on your computer and work on the user interface. that we developed in MATLAB. But we are working on developing a publicly available web-based platform for both the streamlined LCA calculation, meaning when you don't have all detailed data and you have, but you still want to have confidence in your calculation. In addition to a full detailed LCA platform, meaning that you have already collected all your data, but you would like to examine and calculate the environmental impacts of different scenarios in your system. So this is a kind of flexibility that we are building with professional web designers to include the web-based tool and make it publicly available for everyone. The other development that we are working on is about the optimization of pavement segments from a lifecycle GHG emission perspective. Thinking about the examples that Hauran showed from an initial design and maintenance and repair perspective, how can we optimize this instead of sensitivity analysis? We are hoping to work on an optimization tool to minimize the GHG emissions of pavement segments depending on their context. And lastly, now the model has this capacity to accommodate different types of asphalt pavements and jointed plain concrete pavements. We are working on the data collection part to include the continuously reinforced concrete pavement CRCP in the tool as well. Thank you very much for joining this presentation. Please feel free to put your question in the chat box. This is our email address. Feel free to reach out if you want to have access to the tool or if you have any questions about the webinar as well. So I'm going to open the floor for the question to respond to the question. There's a question about the construction activities timing. How did you accommodate the construction activity timings into the model, and what are their impacts? Hauran, would you like to answer that, or would you like me to go ahead and respond to that?
Yeah, you can go ahead, Hassan.
Yeah. So the impact of timing is important for us about those time-dependent parameters such as IRI and carbonation. So these are some of the time-dependent parameters in the model. So we include those timing and the impacts of maintenance and repair properties on those time-dependent activities throughout the life cycle. And we also included, for example, the maintenance and repair strategies that we would see frequently applied to different life cycle pavements, life cycle of pavements in general. And this is based on the data that we have collected from different sources. So one component is, keeping all those dynamic parameters included in the analysis. Second is the importance of considering maintenance and repair activities on those dynamic parameters. And last one is collecting the data about the future possibilities on the maintenance and repair actions of these roads from publicly available databases like long-term pavement performance database or the Federal Highway Administration statistics. Okay, next question, Hauran. What do you think about the application of this tool for other continents or other locations other than the US? Do you think this tool can accommodate those road segments as well? What's your thoughts on that?
Yeah, for now, so we are using the Pavement as a design tool, as also we incorporate all the climate data from the United States, so we can easily extend to Canadian because Canadian had the same climate system and data be available. And for the other countries, so this framework can be definitely easily to extend, but will be accommodated with local climate data and local design practice and the design guide.
Okay, so the only data that they would need is the local design guidelines and some of the climate information about the humidity and fluctuations in the temperature, etc., right?
Yep.
Okay, great. So there is a question about the probabilistic carbon emission calculation. How do you determine the uncertainty bound of carbon emissions over analysis period? Like when
Yeah,
you
so
define maybe talking a little bit about the pedigree metrics and other probabilistic parameters that you introduce to your system.
yeah, so we have the uncertainty as our input data. So if the user do not have the specific input data, or the user has specific input data, but there will be still existing the uncertainties. So we have to implement the pedigree matrix to include the necessary of the uncertainties of specific input data, and to run a Monte Carlo simulations to run like 1,000 Monte Carlo simulations to try to simulate all the potential uncertainties, potential combinations of this input data, and then it will be used as our iterative payment LC analysis. And the result, the payment LC results also will involve those uncertainties as a result of our probabilistic payment LC analysis. And with those uncertainties, which affect our payment results, so those uncertainties was actually introduced from the input data. So yeah, we can accommodate that uncertainty.
That's great. So we have different uncertain inputs. One is the emission factors that we have calculated based on the life cycle inventory and the bill of materials for different mix types and different locations, as well as the bill of activities about the construction emissions. We also have those data collected. Howran included pedigree metrics to propagate uncertainty in those sources. Also, we have design uncertainty and uncertainty relevant to the future of the performance of these pavements. For example, the IRI ranges that will be determining factors for the design, and also the LCA results. This is a separate type of uncertainty, parameter uncertainty that Howran accommodated based on the Monte Carlo simulations and the number of, 1,000 times that he ran the analysis. Great, thank you. Okay, there is another question about the input data from a mechanistic empirical design prediction. What kind of data did you use, Howran?
Yeah, so for perform this payment ME design, so we have performed sensitivity analysis to indicate those sensitive payment design parameters affecting our payment life cycle performance prediction. So include both concrete payment as asphalt payment. So different payment has different set of sensitive parameters. For example, for the concrete payment, we have the payment thickness, pavement material properties, for example, the elastic modulus, and pavement geometry, for example, the joint spacing, slab width, shoulder tabs, etc., which will significantly affect the concrete pavement performance of cracking, faulting, as well as the RI. And for the asphalt pavement, we include the asphalt binder properties, the binder tab, as AC binder tab, the AC binder air voice effective binder contents, as well as the other, for example, the surrogate modulus, the base modulus, and the traffic exactly for both types of pavement. So they're all sensitive parameters based on the ME-PDG definitions, and they all be used for building our pavement ME database for training our machine learning surrogate models. So we have enabled the capabilities of a wide range of data variations for the design of our pavement using ME-PDG design.
Great, thank you for the explanation. Just to sum it up in a few sentences, I would say we use probabilistic triage to identify those design parameters that have the largest influence on the results outcome. So in this way, we make our design process more efficient and applicable to a streamlined LCA tool. And then after identifying those a few dozens of parameters for each pavement type, we ran the artificial neural network in order to make the design happen within the tool and predict the performance as well. All right, thank you. There is another question about the availability of this webinar. Yes, the webinar will be available after this. The webinar is now being recorded and is available on YouTube webpage of CSHub. Feel free to go there and watch it. And for the tool, as I mentioned, the tool is also available. Feel free to reach out to us if you want to try it. Otherwise, please wait for the web-based platform that you're working on and will be released in the next few months. So you can calculate your lifecycle GHG emissions using that web-based tool. I don't see any more questions. I think we are 10 minutes to the hour. I think we are almost done with the time. Andrew, would you like to adjourn us today?
Absolutely. So yes, as Assam mentioned, this webinar will be uploaded to YouTube as soon as I finish processing it. So thank you so much for the discussion. Thanks for your attention, and I hope you have a great day. All right, bye now.
Thank you.